Great. Thank you all for coming. My name is Iain Dunning. I just finished my 4th year of my PhD here at MIT in the Operations Research Center. Operations research is something you may not have heard of, and it's basically, you can think of mainly a study of optimization and probability and mathematical modeling with a particular focus on sort of more business and industrial applications than maybe like applied math, which might consider physics and things. We don't do physics so much, but we do supply chains and making your airline tickets cost more than you'd like, but just enough to you're willing to pay. So that's what we do. That's my details there. And I'm going to talk to you about JuliaOpt, which is an organization that we have created over the past couple of years to house optimization packages in Julia. So when I say optimization, you might not necessarily know what that means in that context, because it means lots of things to different people. In the most generic form, we've got something we want to optimize, F, and we want to maybe optimize it subject to some constraints. X is the thing we're trying to optimize. It represents decisions. It could be real numbers. It could be integers. It could be something more abstract. Usually it's not that abstract. Usually it's something quite tangible. And I consider problems personally with lots of G's, lots of constraints. And to many people, optimization is just minimizing F. So the entire field of machine learning arguably is minimizing various forms of F. Operations research is usually minimizing possibly pretty simple Fs subject to possibly many and complicated Gs. So my bias will probably show through in how I think of what optimization is and what the problems I think about are. But hopefully we can kind of find a middle ground where your concept of optimization and ours meet. And if we haven't got that kind of thing that you want to do, feel free to add it. We're always willing to grow and expand what we cover. So some applications of optimization. These are some pictures taken from a paper we just submitted about JUMP. In this problem, we have a set of facilities that have squares here in a nice grid for ease of demonstration in a paper. And we're trying to locate facilities such that the maximum distance of any facility from a customer is minimized. So the maximum distance is minimized. That's a pretty reasonable thing to do. Maybe we're Amazon, we want to locate facilities so that we can guarantee deliveries are within 2 days for everyone. So we have to locate facilities that are no more than 2 days from any one place. On the right, we have something completely different. This is something we're going to show in the workshop tomorrow, but we have a rocket, and we want to control, it's a liquid-propelled rocket, liquid fuel rocket, and so we can change the thrust dynamically. And the challenge is to find a thrust profile that will guarantee we get to the maximum altitude possible, subject to drag, the fact we're getting lighter as we use up our fuel. And it turns out, as the altitude sort of you go up and you burn and then you coast and you come to a high point and your mass decreases as you burn your fuel and your velocity has this interesting structure where it goes through a sort of change in curve there. And the thrust profile says, burn everything you can for a few seconds, and then cut down your thrust, and then ramp it up again, and then you've used up all your fuel and you stop. So, unintuitive stuff, but if you can mathematically model it, you can probably solve it. This is my attempt at showing machine learning, which is pretty much just variations on separating colored dots. Pretty boring stuff, really. And over here is some work that Madeline Udell, who's is a JuliaOpt contributor, has made the convex.jl package, and this is a paper of hers maximizing a sum of sigmoids, and she applies it to the presidential problem of figuring out who to pander to optimally to get elected. So I recommend you check out that paper because it's a pretty fresh perspective on the problem. Anyway, so that's what kind of things we think about, and what JuliaOpt is packages to enable these things to be done. So we have modeling packages, so ways to express your optimization problems in code in Julia, in a way that's user-friendly. Ways to solve optimization problems, so that's pure Julia solvers, but also wrappers around the wide array of high-performance and well-tested and well-resourced external solvers. And then abstraction layer between all those things, like the glue that joins all these things together. So as an organization, we kind of pride ourselves in having pretty high standards. Julia is like a young language, and so a lot of trust is involved to get people to use it. So we aim for all packages to have support for all the platforms if they have binaries, to have at least some documentation, no blank README pages, tests, and to integrate with the rest of JuliaOpt. So we don't want things to be siloed and just nominally under one umbrella. We want everything to interrupt with each other where appropriate. The website we're trying to build into a more centralized guide to optimization in Julia, and that means examples, documentation, guides, and other resources like classes that are using it, teaching materials. So we have actually a collection of notebooks we're growing, and if you use Jump and Convex, anything in JuliaOpt, and you've got some notebooks you'd like to share, we would love to add them to this repository. We've had some contributions from the community who haven't been package developers, they've just been users, and they've contributed some really fascinating stuff. So these are the packages we have right now. This one's in dotted lines because it's soon to be added. It was kind of in the provisional acceptance stage. We haven't moved it in yet. But at the top, we have Jump and Convex, which are two different ways to model optimization problems. And I'm going to talk a lot about that because modeling is something that's very interesting to me and we've put a lot of thought into. MathProg Base is an abstraction layer that goes between the solvers and the modeling languages and your user code if you want. You can tap into it directly. It's not like StatsBase so much in that it's like a set of common utility functions. It really is like an abstraction layer that you can use as a kind of common set of functions, but it's really about the interface. In the bottom left corner, we have Optim and least squares fit.jl, which are kind of separate from the rest in that they don't directly interact with these packages, but they are, of course, very much optimization packages. Optim is pure Julia routines. I'll cover that later on. And these two packages are pseudo-solvers. They are kind of like solvers that they're kind of a generic way to sort of get optimization problems out of Julia into standardized forms that are used in the community, which can then be used by solvers that we haven't directly wrapped yet or can't even wrap. We don't have access to them for whatever reason. So these are kind of pseudo-solvers, but they're all part of the whole thing. All right, so Jump and Convex.jl. So these are two modeling languages for optimization problems. A modeling language lets you express the mathematical statement of the problem in Julia code in a way that's sort of easy for you to read, easy for you to maintain, and will efficiently translate from that form into whatever form the solver needs, which is usually something that is very much not user-friendly. And they're not trying to be, so that's why the modeling languages exist. So Jump handles general linear, quadratic, nonlinear, integer, constrained optimization problems. It also has some features for advanced integer programming features, so you can tap into these solvers and change how they work, and for doing enumerative sort of branch and bound tree searches. And it also has something that's pretty cutting edge, which is automatic generation of first and second order derivatives for constrained optimization problems. Convex.jl is an implementation of the disciplined convex programming framework rule set mindset. And I'll get into what that means with an example. But it's basically a different road to the same means. It has a different set of, there's an intersecting but not subset level of support for optimization problems. So you can model all these different kinds of problems: linear, second order, semi-definite, exponential code optimization problems, geometric programming, if you've heard of that. That's something that comes into that kind of worldview. And it also has this interesting feature of validating your model in a sense that it will guarantee you, it'll give you kind of a proof that your model is convex. And convexity is a very desirable property to have in an optimization problem. So we'll get more into that later on. Starting off with Jump, so the kind of thing that we use Jump for are things like this. So the left-hand side, there's a min up here that's been cut off somehow. So we're trying to minimize this quadratic function. You'll notice that there are multiple variables. Y is a variable, U is a variable. They have indices. The indices start at 0 and go to n, so they don't start at 1. So already we're kind of an interesting territory for Julia. We have constraints. We have many constraints. The constraints of themselves, this is actually a large number of constraints for every I and for every j in these sets. We have some simple constraints, complicated constraints, all sorts of constraints, variable bounds. And this is the kind of thing that we care about. This problem is a discretized version of a linear quadratic control problem. So this possibly came from a PDE that was linearized on a grid. So this is another optimization problem. Can anyone, well, it's not really an optimization problem because there's no objective. It's more of a constraint satisfaction problem. And can someone tell me what this is? Sudoku? It is Sudoku. So this, I've missed out the constraints that enforce the original solution, but these constraints will give you a valid Sudoku solution. What I've done is I've made a variable xijk that can be either 0 or 1. So I and j refer to the grid cell, so there's 1 to 9 grid cells, and k is a digit that goes in that cell. So the top constraint says that across each column and each number, each row contains, each digit can only appear once in each row. Each digit can appear only once in each column. Each digit can appear, only one digit can appear per cell, so that's the for each I and j, the sum across the possible digits. And then the bottom constraint is that weird one where it says each 3 by 3 square has to have each number once and once only. So that's an integer optimization problem, except there's no objective. We're just trying to find any solution. And what the problem is that that's our Sudoku problem. But what a solver wants is this thing, max min C transpose x, where C is a vector of data, x are decision variables, which is also in a vector form. And it wants the constraints to be in the form of, say, a matrix A times a vector x of decision variables equals B. So it's kind of a standard computational form. But this is not that. For one thing, we have like a 9 by 9 by 9 tensor of variables. We have 729 of these variables in roughly the same order of constraints. And we have to kind of turn it into this A matrix and give it to the solver. And that is what JuMP does. It takes your possibly quite complicated problem and basically boils it down to a sparse matrix, which it constructs very efficiently using metaprogramming to basically generate the code to generate the matrix. So this dot pattern here is the sparsity pattern for that A matrix for Sudoku. So you can see it's mostly sparse, has a complicated structure that you could make by doing a lot of for loops, but I would not recommend it. And God help you if you want to increase the size of a problem to like a generic n by n Sudoku. You're going to have to rewrite the whole thing. So that's what JuMP's all about. It's basically taking your nice user-friendly code and turning it into that horrible matrix. So here's a sort of a taste of what JuMP code looks like. So we create a model. A model is everything is associated with a model. The variables and constraints are all associated with a model. We define some variables. Everything's macro-driven. So this macro def var generates a special JuMP array type, which thanks to the new indexing work, you can kind of imagine how that works. We can kind of make our own arrays and containers. And we can give it some index sets. Here all the index sets are just numbers, 1 to 9. So that's pretty much just an array. There's nothing special going on in this particular example. But JuMP can index by arbitrary sets. So you can give it a list of symbols, a list of strings, a list of objects. You can have as many indices as you want. And we can then say the type of the variable. So this is binary, but it could be integer. It could be just a real. It can be between 0 and 1. It can be between -infinity and 2. It's all good. Then we need to add constraints to the model. So we add a constraint to the model. We're going to iterate over all. So this is we're doing the columns right now. So for every column and for each digit, that should be, that's a V. I used K before. That's just needlessly confusing. So for each column and for each digit, the sum across all rows I, 1 to 9, of x, I, j, v equals 1. And what this does is, you see that sum with the curly brackets? That's not the default Julia sum. That's our own sort of domain-specific language sum. And what it does is it's kind of like sum supercharged. So it lets you do sums over interesting sets. It lets you put conditionals in there, so you can do a sum over only the even i's, for example. If you used array comprehensions in Python, it's essentially that, but inside Julia, inside our own little domain. And this is basically us writing the whole model. And you can see there's a one-to-one sort of translation between the mathematics and the code, which is what we want. And then the final constraint I've added here is just enforcing the original solution. So if we had a matrix Sij, I can just say the value of Xij has to contain digit Sij. And then we solve it. And when we solve it, what JuMP does is it analyzes the problem and says, oh, this is a linear integer program. I need a linear integer programming solver. What do you have installed? Oh, you have CBC. We're good to go. Solve it and return the solution and stick it inside that model object where we can get to it later. So I just found this the other day. Thanks to Iain sent me this. This is another example of a sparsity pattern for another integer programming problem, the n-queens problem for n equals 30. So I think that's pretty cool. So that's one side of JuMP. And JuMP models can get very complicated, tens of millions of variables. And one thing we put a lot of effort into is making that fast. So the time it takes to generate a model when you have tens of millions of variables and millions of constraints is actually non-negligible. And JuMP is as fast as dedicated tools in domain-specific languages that are not embedded in anything else. So dedicated tools for making modeling optimization problems, we're as fast as those. And that is pretty novel in the field of open source modeling tools. So JUMP is really kind of sticking to the commercial modeling systems. So everything I've shown you so far applies to sort of linear and quadratic problems, where the solver wants the problem in a form of a big sparse matrix. But we also handle generic nonlinear optimization problems. And we have to think about nonlinear optimization problems in an entirely different way. So we're back to our original sort of standard form problem. And what nonlinear solvers want are not an A matrix, but they want functions. They want functions that calculate things. They want functions to calculate the values of the objective and the constraints. They want functions to calculate the second derivatives of the functions and constraints. And they want a function to calculate second derivatives. And a couple of the ones we use want actually the Lagrangian relaxation of the problem, the second derivative of that. So we have to take a generic nonlinear optimization problem and compile it basically into functions, or interpret it, but we compile it. But we need to generate these derivative evaluating functions. And we want to do it automatically, because the whole point of a modeling language is that we're saving you from doing work. So if you use these solvers directly, it is up to you to manually calculate the derivatives of your optimization problem, including this monstrosity, and provide it in a sparse format, because most of the values is 0, typically. So here's an example of a kind of thing we do. This is something out the front here. It's a sum. There's a sum over k. And this is the objective function for an AC power flow problem. So you have a power grid, and you're trying to basically decide the power flow along each arc and the phase angles at the buses and whatnot. And AC is all wavy, and so it's very nonlinear. So we have causes, sines. These g's are actually not just constants. That's actually a function. They're functions themselves of variables. G's a variable, theta's a variable. There's squares at the front, squares of sines and pluses, and oh my goodness, very nonlinear. But JUMP's all right with that. So this is this constraint translated into JUMP. And you can see that while it is long, it is pretty readable and, more importantly, debuggable. So I had to translate this actually from another language, so Miles translated it to JUMP, and then I had to translate it to another language, and it looks like spaghetti in the other language, but I was quite happy with this, and so it was a good reference. But you can see here we've got the sum, outside sum, and that's over k and 1 to the number of buses. And we've got a condition which is denoted by the semicolon. After the semicolon, we have a condition saying that the bus type has to be 2 or 3. So we're doing a sum over all k such that this condition holds. And for the k which condition does not hold, we will skip those k's. Inside the sum, we have an inner sum. It's just a simple sum over a list. But you can see that the inner list is indexed by the outer thing. So, creating quite complicated expressions. And we're just using cos and sine and multiply and everything else. Just pretty much plain Julia, apart from the magical sums. So to learn more about automatic differentiation, we recently submitted a paper that you can get to from the JuliaOpt website. It's quite a deep topic, and I don't have time to go into it. But our automatic differentiation implementation is competitive, basically, with the best of breeds out there. The only condition that we have, and this is possibly a problem for some of you, is that the functions, the constraints, and the objectives have to be provided, they have to be analytical. You have to be able to write it out in sort of closed form. So if you have a kind of a black box function, we aren't able to automatically differentiate that yet. So you have to be able to kind of write it out as like a nice mathematical statement. Possibly with sums, possibly with conditions on the sums and whatnot, but not a general black box problem. So convex.jl is a different modeling tool that is also part of JuliaOpt and has a different perspective. So it's this thing called disciplined convex programming. And the idea is that, this is a quote I took from the website, DCP is a system for constructing mathematical expressions with known curvature from a given library of base functions. So what it means by curvature is sort of fixity. So this set is a convex set. We can't find 2 points that are in the set such that any line between the 2 points is outside the set, which is not true for this lovely little shape here, where we pick these 2 points, and there are some points between them that aren't themselves in the set. The problem is, for this one, in general, we can't say anything about if we've found the optimal solution. Because we might start here and start working our way down and find a solution here and think, oh, great. But we could have possibly gone down this way as well, and we wouldn't know it. So there can be many optimal solutions, or we can just get stuck in a solution we think is optimal, but it isn't. It's locally optimal. So convexity is a very nice property. And for things that are linear, it's usually very obvious that they're convex. A lot of things that I personally do, it's kind of fairly obvious that they're convex. But there are many problems in many domains that are convex, but are not obviously so. And what convex.jl will do, or attempt to do, is show that the problem is convex, even if you put it in quite an interesting, non-obvious form, and reduce it to a more simple problem that a solver can understand. So it can't necessarily handle all possible convex problems, but can handle a lot of ones that are of interest. So here's my example to kind of motivate this. This is taken from Stephen Boyd's convex optimization book. So given a polyhedron C, which we've been given as a form of the lines, the outside lines that define it, this line, this line, this line, this line, and given a polyhedron C, we want to find the ellipsoid E, which we can express in this form of a B matrix that kind of shows you how it's skewed, and D, which is the center. We want to find an ellipsoid of maximum volume that is contained inside the C, for polyhedron C. So like in this case, it would just be a circle that's sort of inscribed by a polyhedron, but what if it's a weird, more wonky shape? So we can express this optimization problem in the following form. We can say, maximize the log determinant of B, subject to this constraint that basically says that the ellipsoid is always inside the polyhedron. So why are we maximizing the log determinant of B? So the determinant of B is the product of the eigenvalues, which you can kind of think of as like how far we're stretching in each direction. And the log determinant of B you can basically think of as a proxy to the volume. I don't know, I can't remember if it's like an upper bound and volume or whatnot. Let's just say it's the volume. I don't want to get myself saying something stupid. So that's what we want to maximize. This is basically equivalent to this problem here. But the problem is it's not super obvious to me, at least when I first looked at it, that log det B was itself a concave function. So we're maximizing. So we want a function that's kind of like an upside down shape. So if we go up, we know that we're always going to hit the best possible volume. So we can write out that constraint in a more nice form. And now we want to ask, is that objective concave? So B is a positive semi-definite matrix because we've got an ellipse and we kind of, the eigenvalues correspond to the stretching in each direction. So B is positive semi-definite. OK, that means all the eigenvalues of B are non-negative. Determinant of B is just the product of the eigenvalues of B. So that's good. So we're taking the product of a whole lot of positive or non-negative numbers. OK, so this part's positive. The log of a positive number, well, you might have noticed that all the eigenvalues could possibly be 0, in which case it'd be screwed. But let's pretend that doesn't happen. But the log of a positive number is concave. That's pretty simple. Draw a picture of, or plot log in Gadfly, and you'll be convinced of that. So we've basically proven to ourselves that this is overall a concave function. And what that lets convex do is that it will itself work that out. So we can, So we define a variable, trust me on this one, we define a variable B. So B equals variable, a 2 by 2 matrix. D is a vector of length 2. Our problem is to maximize the log det of B. So log det of B is defined by convex as like a function that can operate on variables, and it kind of tracks the convexity or concavity of that function as it goes. Then we add each of the constraints to the model. We say the norm of B times A plus A transpose D is less than or equal to B. That's just this, less than or equal to 1. We ilv it, and we intlen it, and then we get our solution. And it turns out that for this polyhedron here, defined by the interior of all these, the intersection of all these half spaces, is a slightly skewed ellipse. So That's pretty magical. So the question then you may be wondering is, which one do I use? This is all so great. I'm going to go home and play with it. What am I actually trying to do here? And here's a rough guide to how you might want to think about it. So convex, if you suspect your problem is convex, but it's not obvious how to transform it into a simpler form that a solver can handle, you want to be using convex, because its whole job is to do that for you. If it's nonlinear, like this problem, but has some sort of structure you suspect is there, convex.jl will exploit that structure possibly better than jump can, because jump doesn't do transformations of the problem. However, if you have a problem that has sort of complex indexing schemes, so 3 or more dimensions, your indices aren't simply 1 to n, you want to index by airports or something like that, which we will do tomorrow. If its problem is nonlinear and non-convex, you have to use jump. If it's quite large scale, so hundreds of thousands of variables, then you definitely want to be thinking about jump, which is sort of more tuned to sort of high-speed generation of models. And if you want to kind of mess around with a solver by customizing it, jump exposes those features. So for solving the problems, we have a wide range of solver interfaces. So they all kind of do different things. So we have mixed integer linear programming solvers, like CVC, CLPs, LPs, Cplex Groby for mixed integer and mixed integer quadratic. ECOS is for second-order cone problems. GLPK, linear programs, integer programs. Nitro and Mosec are aimed at nonlinear optimization. Mosec does a little bit of all these. NLOpt is meant for kind of more simply constrained problems, but can handle pretty much anything you throw at it. It has a wide variety of algorithms that can handle some pretty pathological things. And SCS can handle linear programs all the way up to semi-definite optimization. And of course, if you don't have to worry about all of these constraints, then optim.jl is your friend, or maybe even least squares fit. So I want to get back to mathprog base, which was the interface to all these solvers that jump and convex both go through. So jump and convex do not concern themselves with the details of any particular solver. You can swap out the solvers and jump doesn't care. And it does this by using the mathprog base standard interface for optimization. Wow, there's some words missing. And I would say it's pretty much been crucial to the success of mathprog base, because the feature that wows a lot of people in this field is that they might write code that uses a particular solver's interface. And it might not be that bad, but then for whatever the reason, they have to use a different solver. And now their code base is trash. So if you buy a Cplex license from IBM, and one day they jack up the price and you don't want to pay Cplex anymore, well, you're screwed, because you have to rewrite your whole interface to the solver when you switch to someone else. It might not be too different, but that's time you're wasting when you could be doing more profitable things. So the interface is actually broken down into multiple parts. There's parts that relate to linear programming, mixed integer programming, quadratic programming, conic programming, callbacks, nonlinear programming. They each kind of define a set of functions that a solver can implement, and you can kind of, if you have a new solver and you want to use it from jump, you can kind of keep trying to use the solver with jump and implementing methods until it works if you want. The minimum set is quite small, but there are a lot of things that are optional, like you can solve the problem, maybe modify the data and resolve efficiently. You don't have to implement that part of the interface, but if you do want to implement it, jump can use that to more efficiently do resolves, for example. I put semi-definite programming in gray because it was in the interface, but we've kind of backpedaled on that and included it in the conic programming interface now. And that kind of brings me to, I just wanted to share some maybe lessons learned when we've made mathprog base that might be of interest to people who don't even particularly care about optimization. So remember, mathprog base is an interface over 10 different solvers, none of them made by us. And basically, we had to abstract over that. And a key thing that we tried to do was not create an interface or abstraction over a sample size of 1. And that might seem obvious, but you might sort of be tempted to think, OK, these sorts of problems look like this. If you try and abstract too soon, you tend to make mistakes in that abstraction. So we didn't callbacks. We had solvers wrapped that had callback support early on, but callbacks are a kind of newer feature in integer programming, and there's quite different styles in handling them. For example, one of the solvers For each different state in the solve process, it wants a different callback function provided. Okay. The other solver wants one callback, and it will give you a flag telling you what state it's in. That's the kind of thing that users shouldn't need to care about. So when if we had designed the interface straight up, we might have made a mistake and made it impossible to add the second solver that had an entirely different view. So this is why we're sort of saying, if you're abstracting, have a sample size of 2. And SDP, we kind of thought maybe we had a sample size of 2, but we kind of didn't really at the time. And so things kind of became apparent that we weren't quite right. And then at that point, you kind of have to throw it out and start again. So that's a cautionary tale from our experiences. But the benefit of it is that once you've got the interface up and running and it's kind of got some gravitas and people respect it, new people can come along and tap into it and get all the benefit of it. So Jump was kind of the initial modeling language in Julia, and we made MathFrog-based to support Jump. Convex.jl came along later, and to get up and running in Bootstrap, they were talking to solvers directly. But once they kind of got established, they were able to connect to MathFrog base and use that interface. And suddenly, they're using all these solvers when before they were using, 1 or 2. So that's kind of the promise, and that's kind of on the consumer side. But if you're a solver and you have a solver you want to use in your work that we haven't wrapped yet, you can go ahead and wrap it, implement the interface, and everyone will immediately benefit from having your solver wrapped. So it's quite a powerful incentive to contribute back, because everything you kind of add is instantly usable by everyone, and you can use everything. Another neat thing you can think about is that since we have all these solvers implemented, you can kind of develop entirely new solvers in Julia. So we don't actually have any pure Julia solvers, complicated solvers written in Julia that are part of JuliaOpt yet, and I'm hoping that'll happen one day when the need is there, because a lot of these external solvers are very good, and it's not super clear you need to reinvent that wheel. But there are some new sort of more edgy problem classes that are kind of hot topics in research, and there aren't really this established bed of solvers, so maybe you need to make your own solver. Well, one kind of problem that's caught my attention is mixed integer, non-convex, quadratically constrained optimization problems. And this is a mouthful, but it occurs a lot when you are blending things. So if you're like a refinery and you're piping fluids through pipes and into tanks and then mixing, you get a lot of non-convex products of variables. And you might have some integer decisions about whether to build a certain set of pipes or reactors. And then after you've decided those integer decisions, you kind of have to deal with the consequences of those decisions, and those are captured by combinations of continuous numbers in a non-convex fashion. It's a tough kind of problem to solve, and the kind of sizes of problems you can solve are like 300 variables instead of 10 million. So how do we solve them? Well, one way to solve them is to solve them as a succession of relaxations that are themselves easier to solve. So the kind of flow you can imagine is that you model the problem in Jump, which can model these problems fine. It doesn't care that it's not easy to solve. Jump will kind of boil it down into a standardized form, pass it through MathFrog base to your new solver, which you've written in Julia. But your solver is not really doing a lot of mathematical heavy lifting itself. It's really just an organized way to solve a series of relaxations, in this case mixed integer linear programs, for which you can use any of the other linear programming solvers that we have installed. So basically, you can create pseudo solvers to experiment with new ideas very rapidly, because you don't have to worry about the glue for taking in the model, which is annoying. You don't have to worry about producing glue to interact with interior solvers. I can swap out the interior integer programming solver at will. Maybe I have a commercial license one day, I can use a better interior solver. Maybe I don't the next day, I can swap it out with an open source one. The thing is, you've managed to sort of detach yourself from these earthly concerns. You can only think about lofty convex relaxations. And how great is that? So that's sort of the end of the constrained optimization story. I just want to sort of quickly cover optim.jl, which I haven't personally worked on a lot, but is very important to a lot of people. And basically, it's pure Julia implementations of optimization routines for unconstrained or sort of boxed simple constrained problems. And it's got all the classics: BFGS, Levenberg-Marquardt, Nelder-Mead, etc. Simulated annealing, I think, is in there as well. And you can provide, basically you provide a function to evaluate. You can also provide derivatives if you have them. And one of the cool things I think is that you can actually provide a function, and if you write it with some care, Optim can automatically calculate exact derivatives, not approximate, exact derivatives, and solve using those. So this is an example of a Rosenbrock function. It's kind of a known, entry-level challenging problem for nonlinear optimization solvers. This kind of trench of blue makes it kind of get lost. And damn it. What we've got up here is a generalization of the Rosenbrock function for 100 dimensions. That's a pretty nasty function. And what I've got here is calling optimize, which is provided by Optim, on this function. I'm using the LBFGS algorithm, and I'm starting at the origin, all zeros. And I provided the function Rosenbrock 100, and I'm limiting them both to 21 iterations of this algorithm. But the difference is in the second one, I'm saying autodiff equals true, please. And what it does is it uses this technique uses this thing called Joule numbers, which are basically a way to simultaneously evaluate the function and get its derivatives. So that function up there, you notice it takes in a vector, but it doesn't say vector float 64s. It's basically just saying, give me vectors of something. I could have been more specific and said number. And you can see that out, I carefully did not set equal to 0.0. I actually set it to the 0 of the element type of the vector, type stability. And then I calculate the function as per normal. It doesn't look anything weird, but these Joule numbers are a different number type that basically implements some, it's kind of like complex numbers. Basically, it's a lot like complex numbers. There's like a real part and there's a Joule part. And via math, you get the derivative if you run these through the function. So you can see that with 21 iterations without the derivative, it takes 0.04 seconds and is nowhere near the optimum value. It's got an objective at that point of 3.4 seconds, 3.4. Whereas with the auto differentiation provided, we actually solve it in 21 iterations to tolerance, and it takes less time to get there. So derivatives are important, and you don't have to necessarily do them yourself if you're careful, and I think that's pretty neat. So to finish off, building on JuliaOpt is kind of encouraging to see that the package ecosystem is sort of using JuliaOpt now as a component. There's a large list of packages that are using Optim for a variety of needs. There's a couple of packages using jump optionally. So Gadfly/Compose will use it to lay out text labels, if possible, on your plots. And GraphLayout.jl is something I've made to kind of like GraphViz. And for the tree layout algorithm, we actually optionally uses linear and integer programming to calculate more aesthetically pleasing layouts using the power of optimization. So I've got a crane up there. We're extending it in the other way. We're making jump more powerful by extending it to new problem classes that are kind of more on the frontier of research. We have robust optimization, chance constraints, and stochastic optimization, all to do with uncertainty, actually, different paradigms, which is kind of funny. And Ian, Miles, and Joey, we all have our own ones. And finally, JuliaOpt is obviously taking off in a variety of ways, but we're very excited about. I don't actually know all the universities that are using it, and we really need to do a better job of collecting that, but it's at least 5 or so that we know for sure, being used to teach people. The number of papers not written by us about JuliaOpt is increasing, which is encouraging to see. I just found out about one today. Mike Jordan at Berkeley, big machine learning guy, just put something up on Archive. These are all using jump for a variety of tasks. We know a few companies are using it, but the only one we know for sure and is a big booster of us is StaffJoy, Philip Thomas. He's been advocating jump for anyone who will listen, which is great. And obviously this information will be out of date soon, so if you want to kind of keep track on who's using it and keep track of materials and things you can use yourself, please keep checking in at JuliaOpt.org. And thank you to our contributors who have made it all happen. There's a large list and we want it to grow, so please, if you're interested in this field, get in touch and see how you can either contribute code you've already written or participate in maintaining these packages. Thank you.